Yesterday, where we sort of left off was we talked about the remainder theorem, which essentially gave us the remainder when some polynomial p of x was divided by x minus a. We could get the remainder by just plugging the a value into the polynomial. And that's really nice because if we're only after the remainder and not the quotient, we can just sub in to get the remainder instead of having to do the whole long division or synthetic division. Okay? And where this is really all leading to is something called the factor theorem. And the factor theorem essentially states that if you divide some polynomial by x minus a and the remainder is 0, what do you think that means? What do you think that means? I think I talked about this a little bit yesterday when I said, let's say we do 21 divided by 3. 21 divided by 3 is 7. There's no remainder. Yep. Yes, it means that it's a factor. Right? Then x minus a is a factor of px. Okay? So ultimately, in terms of why we do this synthetic division, long division, remainder theorem, it's all for this point. If we can figure out a factor of the polynomial, we can slowly start to pick it apart so that it is entirely factored into the smallest of parts. Okay? Similar to when we're doing, let's say, prime factorization. And we take the number, let's say 100. We don't write the whole prime factorization at first. We break it into two factors. We go like 2 times 50. Then we break the 50 down and go 2 times 25. And we break the 25 down and do 5 times 5. That's what we're going to be doing with polynomials. We're going to try and use this factor theorem to figure out one factor of the polynomial. Then when we divide out that factor, we'll have a smaller quotient to work with, and we can start to factor that as well. Okay? Once it gets to a quadratic, ax squared plus bx plus c, then we have other strategies to factor it other than the factor theorem and synthetic division. Okay? So for example, let's just say we wanted to know if x minus 1 and x plus 3 are factors of p of x. Okay. We can look, if this is our x minus a, okay, we can look at the value of p of a. And if p of a is equal to 0, then that's a factor. Okay, so for this guy, I'm going to look at p of 1, and that is 1 cubed plus 2 times 1 squared minus 5 times 1 minus 6. So that's, let's see, 1 plus 2 is 3, minus 5 is negative 2, minus 6 is negative 8. Okay? This is our remainder. Since we get a remainder that's not 0, we can conclude that x minus 1 is not a factor of the original polynomial. Okay? The remainder does not equal 0. Therefore, x minus 1 is not a factor. Okay. Now we're going to do the same thing for this binomial, x plus 3. This time we have to sub in a negative 3. Because if x plus 3 is x minus a, that's x minus negative 3. So we're also going to look at p of negative 3. And that is negative 3 cubed plus 2 times negative 3 squared minus 5 times negative 3 minus 6. And that is, let's see, negative 27. Now this is 2 times 9, so plus 18. And then this would be plus 15 minus 6. And I believe that equals 0. How do I know which? Oh, how do I do it so fast in my head? You guys, I do this all day, every day, for hours and hours and hours. Oh, yeah, like how did I know that this was going to work? Is that what you mean? Oh, just this part? It's like my party trick. I don't know. This is 33 minus 33. That's kind of how I look at it. But you know what? Don't worry about that. You can use a calculator. It's not a problem. Okay? The remainder is 0, so x plus 3 is a factor. Okay? Now, we're just kind of trying to understand how we can use this factor theorem to get a factor. I want to talk a little bit about, like, how do you know what to test, right? How do you know what a value to test? And then we'll actually try and factor an entire polynomial. Okay? So the integral is zero theorem. So this is going to help us to decide what should these a values be? What could be a possibility? Okay? And the integral zero theorem states that if the polynomial p of x has a leading coefficient of 1, and suppose x minus a is a factor of this polynomial. Okay? So if the leading coefficient is 1 and x minus a is a factor, then a must be a factor of the constant of the polynomial. Okay. Now, to show sort of what this means, I want to just remind you of what it would look like if we were working with a quadratic, because we have lots and lots and lots of practice factoring those. Okay? So let's say I took something like x squared minus 7x plus 10. Okay? And that is going to have a factor x minus a. Okay? What this theorem states is that that x minus a, whatever that a value is, has to be a factor of 10. So, you know, we do this all the time with factoring. What could it be? It could be 1 and 10. It could be negative 1 and negative 10. Has to multiply to 10. It could be negative 2 and negative 5, or it could be 2 and 5. Okay? Now, that's something that we've already sort of practiced when we factor these guys, because we know through expansion, right? The ones that work in this case are x minus 2 and x minus 5. We know by expansion that we get that constant by multiplying all of the a values together. And so if an a value is going to work, then it has to be a factor of that constant. Okay? Now what this does is it narrows down the playing field, because, you know, if this constant is negative 6, then the only numbers that could work, that we could test with the factor theorem, is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay? Now that's still 8 values, but it's a lot less than if we didn't know that, right? If we didn't know that, we would just sort of be, you know, shooting into the wind. We would have no idea where even to start. Okay? And it would take a lot longer. Does that make sense so far? Okay, so what is the factored form of this polynomial? And how can you use the graph of the corresponding polynomial function to simplify your search for integral roots? Okay? Integral roots essentially means the roots would be an integer. So for example here, if the corresponding function y equals x squared minus 7x plus 10, the two roots, or the two zeros, would be 2 and 5. Okay? Well, to start, we need to make a list of possible a values. Okay, so suppose x minus a is a factor, then a could be, could be essentially positive or negative factors of 30. Okay, so could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6. Okay, 6, 7, 8, 9, 10, plus or minus 10, 15, right? And 30. Plus or minus 15 and plus or minus 30. Okay, so if we were trying to use the factor theorem, we would want to evaluate p of 1, p of negative 1, p of 2, p of negative 2, p of 3, p of negative 3, until we get one that's 0. When we get one that's 0, we know we have a factor. Okay? Now, this can take a really long time, particularly when your constant has a ton of factors. Because this is like what? 1, 2, 3, 4, 5, 6, 7, 8, so 16 different numbers to try. Okay? So you can actually sort of quote unquote cheat a little bit by using the graph to help you know what the factors are. Okay? Now, that is not an algebraic solution. So what I would do is graph it, and I actually already graphed this one. So here is y equals. Okay, there's the function. I'm going to look at the graph, and you don't even have to find the zeros on this because these are just numbers that you're going to test. You know, so if they happen to be irrational and off a little bit, when you test those values, then you'll figure that out anyway. Okay? But from this graph, let's see, it looks like we've got a root at negative 3, a root at 2, and a root at 5. Okay? So I'm just going to do a rough sketch of that. It was negative 3, 2, and 5. Okay, it was something like that. Okay, so you know, if this is an algebraic solution, you don't show that part, but then you're like, oh, okay, a good number to check would be p of negative 3, because then you're going to show, okay, yes, I've proven through the factor theorem that this is in fact a 0. Or you could use p of 2 or p of 5. Any of those will work. Okay? And the idea is that you find a factor, factor it out using synthetic division, see what's left, keep going and going and going until eventually you get down to a quadratic. When you have a quadratic, you can just factor it yourself. Okay? Now, let me ask you this. Let's say we have a cubic function. How many possible factors could we have? 3. Yes. So a quadratic function has a potential of 2 possible factors. A cubic function has a potential of 3. A quartic function has a potential of 4. That doesn't always mean that there are 3 factors. Okay? Because, you know, for example, even just think about a quadratic. If you graph a quadratic, you may have no zeros. Or you may have zeros that are irrational. And so those are not going to lead to factors. So we could have a maximum of 3 factors if it's cubic, but we may not get 3 factors. We may get less than that. Okay, so here's what we're going to do. Let's just pick one of these. Let's say we're doing, I don't know, p of 2. That's a nice number. Then we're going to get, okay, that's 2 cubed minus 4 times 2 squared minus 11 times 2 plus 30. Okay? And that works out to be 8 minus 16 minus 22 plus 30. Okay? And that is 0. Okay? Well, okay, so the possible factors have to come from this list, right? But it's going to be really annoying to have to start from square one and test every single value. So what I'm doing is I'm graphing it so that I know what one of the values are, one of the A values that will work. I picked 2 arbitrarily. I could have picked either of these. It doesn't matter. We just need to show algebraically that we've found one, we can factor it out, and then find the others. Okay? All right, so yeah, the 2 is just picked arbitrarily. And what I would actually recommend that you do, although you guys mostly don't have an issue with this, is if you can pick a positive value, pick that, because sometimes people make mistakes when they're squaring, cubing, whatever, negative values, right? Okay, anyway, we've got this factor. So what we know is x minus 2 is a factor. Okay? Now, where we would go with that is we'll say, okay, well, if we take out the x minus 2, what's left? That's like when I'm saying when I prime factorize 100 and I split it into 2 times 50. Well, 2 is a prime factor, but now I got to work with the 50 and break that apart. Okay? So what we're going to do now, and I'm just going to do it here because I'm running out of space, is I'm going to see, okay, let's say I factor that out. What would be left? So I'm going to do synthetic division now to see what's left. So I'll put my negative 2 out there. And then I'm going to copy the coefficients of the terms, 1, negative 4, negative 11, 30. And bring this down, negative 2, subtract, negative 2, 4, subtract, negative 15, 30, and this is now 0. Okay, now that just confirms, okay, yes, it is a factor, but what I'm really interested now is this part. This represents x squared minus 2x minus 15. Okay, now that I can factor. This is x minus 5 times x minus 3. So now once I've got it down to a quadratic, I can find the other 2 factors. When I put it all together, the fully factored form is x minus 2 times x minus 5 times x plus 3. Okay. Now, what do you guys need to show? Because, you know, I would recommend using the graph to help you find one that works, because otherwise it's going to take a really, really, really long time. Okay? So what do you need to show? You need to show the possibilities. What could the A value be?
So we just get that from the x intercept.
Yeah. Well, no. The possibilities are the factors of 30.
Yeah.
The one that works you get from the x-intercepts. Yes. Yes.
On the actual equation, you said x minus 5, x minus 3.
Oh, it's plus. Thank you.
Yeah, because you got
Okay.
the section.
Yes. There we go. Yeah, it's a plus. Thank you. Okay, so let's actually just write this all down, okay, in terms of what are you expected to show? Yes?
So the possibilities are just the factors of 3?
The factors of 3? 30, yes. Positive and negative, yes.
Couldn't you just look at the roots and see, or does that not work yet?
Okay, so you can look at the roots, but that's not an algebraic solution.
Yeah, but like, is that always like true though? Like, would that be a way to check?
Yes, yes. The A value will be the root of the corresponding function. Yes, that is true. Yes.
Maybe these like there's a lot going on here, so maybe please summarize and just like in
Yes.
steps.
That's what we're going to do now. Yes. Okay. So what is the fully factored form of this? Okay. So first thing you need to do is list possible A values if x minus A is a factor. Okay. Now, leading coefficient's 1, so we can just look at the factors of 18. Okay, so the possibilities in this case are plus and minus 1, 2 works, plus and minus 2, plus or minus 3, 4, 5, 6, 7, 8, 9, and 18. Okay? So you got to list those. Then what you need to do is find a factor. Now this is where, I mean, look, we could start putting any of these into the polynomial to see if we get 0. But to save time, what I would recommend that you do is use the graph to help you find one that you know is going to work. Okay? So that you don't have to just test, let's see, that's like 12 different numbers. Okay? So here we're going to test the different possibilities. To find an A value. For which P of A equals 0. Okay? Now here is where you put a little asterisk and you say graph it so that you can get it right on the first time. Okay? So you can kind of like cheat by graphing the corresponding function. And the A values that are going to work are going to be the zeros of that function. Okay? You don't have to do that. You could just test all 12 of these until you find one that works. Right? There could be up to 4 that work. So hopefully you'll get it right on the first or second or whatever, third time. But let's graph it. Okay, so I'm going to clear this one. And I'm graphing x to the 4 minus 3x cubed minus 7x squared plus 15x plus 18. Okay, and I'm just going to hit zoom standard. Shh. Okay, so let's see. Doesn't really matter if you see the relative max or mins because all we care about here are the zeros. So it looks like we could use -2, -1, or 3. Okay? So if you just graph it and say, well, I know that these are the 3 factors, that's not an algebraic solution. What you have to actually do is show through the factor theorem that one of these is in fact a factor. Okay? So let's say we choose -1, P of -1. Okay, now I'm going to evaluate that. So I can't remember what it was. There it is. P of -1 is going to be -1 to the 4 minus 3 times -1 cubed minus 7 times -1 squared plus 15 times 1 plus 18. Okay, and that is, it's 0, but let's just make sure. Okay, so that's 1 minus 3 times -1 plus 3 minus 7 times 1 minus 7 plus 15. Uh-oh. Oh, I put a 1 in there instead of a -1. Okay, that's why. Okay, so this is minus 15. And then plus 18. And that is 0. Okay? So we've got a factor. X minus 1 is a factor. Okay? So actually, this is sort of the second step. Oh, actually, no, I wrote it down. You're finding one that works, right? Find an A value for which P of A equals 0. Okay? Yes. Yes. X plus 1. Okay, I'm going to try very hard not to mix up my positives and negatives for the rest of the day. I can't promise more than that, but for the rest of the day. Okay, so now what do you think we need to do? Yeah. Yeah. The long division, because we want to know, okay, it's like saying we're prime factoring is 100, factorizing 100. So we know that 2 is a prime factor, but what else is left? Okay, so we need to, in step 3, use synthetic division to factor out the x plus 1, and then essentially we have to keep going. Until everything's fully factored. And you kind of have to repeat the step 2 and then the step 3, the synthetic division, over and over until you get it down to quadratic. So if it starts as a polynomial of degree 4, you could have to do it twice. Right? If it starts degree 5, you could have to do it 3 times because you're factoring out 3 factors. Then you get down to the quadratic, you can factor directly. Okay? All right, so we're going to factor out the x plus 1. So I am just going to put the plus 1 here, and then I'll write all of the coefficients, 1, negative 3, negative 7, 15, and 18. And I'll do my synthetic division. So this is a 1, 1, negative 3 minus 1 is negative 4. This is negative 4. 7 minus negative 4 is negative 3. Negative 3. 15 minus negative 3 is 18. 18, 0. Yes? Okay, so the root is negative, but you can do synthetic division by either keeping this sign as is and then doing subtraction in this line. If you did change it to a negative 1, which, you know, it's kind of 50-50 how people do it, then what you would do in your synthetic division is you would add these 2 lines instead of subtract. Okay? All right, so what do we know from here? What we can take from here is that we've partially broken down this polynomial. And the way that we've partially broken it down is this factor, x plus 1, times that, x cubed minus 4x squared minus 3x plus 18. That's where we're at. Okay? So now we have to keep going with this part and find a factor of that. And we know from the graph, we can use the graph again to sort of quote unquote guess one that will work the first time. So let's see. Whoops, where'd my graph go? There it is. Okay, so let's see. Another one that will work is either negative 2 or 3. I'm going to put in the 3. Yes? No? You okay? I'm going to put in the 3. You can pick whichever one you want. Okay, so now I need to work with this. And if I work with that, I know, okay, P of 3 is 3 cubed minus 4 3 times 3 squared minus 3 times 3 plus 18. Okay? Now we know that this is going to end up equaling 0 because we've looked at the graph. But again, if you're using the graph to find these values, that's not an algebraic solution. Okay? And also another reason, besides for just showing that you can do it algebraically, is that we do this kind of factoring all the time in calculus. And in calculus, because something interesting happens when either a polynomial equals 0, or something called its derivative equals 0, or something called its second derivative equals 0. And so we are very interested in being able to factor. And so we're going to use this process of the factor theorem plus synthetic division to break it down. Now, in Math 31, in calculus in university, you don't get a graphing calculator. So yeah, in those courses, you got to test all 12, where are they, of these. It's a pain. Now, the good news is that in those courses, we don't tend to give you ones where you're going to have to test more than 2 or 3 before you find something that works. Okay, but you could have to do it. Yes?
So it's sort of relevant. If you do calculus next semester, like university, right?
If you do calculus next semester, yes, you do.
You still do?
You do.
It's so much easier because you're gonna have
Yeah. So we're getting off topic now, but the question was, if you do calculus next semester, do you have to take it in university? The answer is yes. If you take AP calculus and do the AP exam, then you can get university credit for that. But essentially, Math 31 covers almost all of the first semester of calculus in university, plus a little bit of the second semester. And a lot of universities these days are offering 2 different options for students in first year calculus. One is for students who have never taken calculus before, and one is for students who have. Not all universities do that, but typically the one for the course that you haven't, it's more time and extra credit. So it wouldn't be like a 3-credit course, it might be a 4-credit course. Yeah, okay? All right, so we found another factor, okay? If this is 0, x plus 3 minus 3, sorry, minus 3, I said plus, but I wrote minus, is a factor. Okay, so now we got to break the trinomial that's left, this trinomial factor down, knowing that this is a factor. So we're going to do synthetic division again. This time we're dividing by x minus 3, and we're working with the cubic polynomial. Okay, so we're going to bring this down. 1. 1 times negative 3 is negative 3. Negative 4 minus negative 3 is negative 1. 1 times negative 3 is 3. Negative 3 minus 3 is negative 6. And negative 6 times negative 3 is 18. This is 0. Okay? So at this point, where we're at is, okay, we have that original factor from step 1. We have this second factor from the second time we did the factor theorem and synthetic division. And now we have this left, and that is a quadratic, x squared minus x minus 6. And at this stage, you can factor that quadratic directly, if it's factorable. Okay, so this works out to be x plus 1, x minus 3. And then we're looking for 2 numbers that multiply to negative 6 and add to negative 1. So that's x minus 3 and x plus 2. Okay, so there's actually 2 factors of x minus 3 in here. I'm just going to fix that. Yes?
So the work you want on the test is for us to do this for every single root that we see on our top.
Correct. Until you get down to a quadratic. Once you get down to a quadratic, you can just factor it.
So could you basically just choose any root other than 1? Because if you're just dividing, you get the same answer.
Any root other than 1? You mean for this second step in terms of what you're choosing?
Yeah.
Yeah, so we already did the negative 1 root, so now I'm doing the 3 root to find another one. Yes. Yeah. Yes.
Couldn't you just use what you see on your calculator and just put those directly into your
You could, but that would be a graphic solution to factoring this polynomial. Right? Now again, we're using the graph. You have to show the process. But you can use the graph to help you. Essentially, what you're doing is, okay, I have to Like these are the possibilities that I got to test in terms of subbing into my polynomial, right? So where do I start? It's a bit of a crapshoot unless you use the graph. So you're going to use the graph to help you make like an educated guess. Yes?
So after you like do the first graph and then you find that the first thing is a factor, would
Yes.
you then use like the second equation's constant for the factors?
Yes.
Go back to the first.
So then you're going to work with this guy.
So then you would just use like the A's as factors and then
Yeah. Yeah. Yes.
This is for the leading coefficient is 1.
This is for the leading coefficient is 1. Let's talk about that.
Yeah.
Okay, what if the leading coefficient is not 1? Well, okay, so first, let's just talk about that. So we know with a quadratic that if the leading coefficient is not 1, we can't just put, when we find those two numbers that multiply to a times c and add to b, we can't just put those right into the two brackets, right? We got to do something else. So you may use guess and check. You may do decomposition. That's usually the most common. But it's not like you can just slot them in, right? So for example, if I'm doing, I don't know, 2x plus 1 times x minus 5, that's, what is it, 2x squared minus 10x plus x, so minus 9x, and then minus 5. Okay, so we can't just slot that, like if we find, okay, what multiplies to negative 10 and adds to negative 1, okay, well the two numbers that work are, negative 9. Nothing multiplies to negative 10 and adds to negative 1. The two numbers that will work are negative 10 and 1. Okay? It's not like we can just stick those right back into the brackets. We got to do something else there. There's a little bit more to it. Yes?
Is there like, are we supposed to do the double x minus 3 in the last question? Like if it said like solve it graphically on a test?
We're going to talk about that. Okay, actually, I'm going to answer that question. We're going to go into more detail tomorrow. So there are two factors of x minus 3. Okay? Now, when you look graphically, we only see the 3 zeros. Okay? However, yes? Yeah, it's because it doesn't pass through the x-axis. So when you have, it's called a 0 with multiplicity 2, meaning that there are two factors of x minus 3. What you will see graphically is the graph will hit the axis, but not pass through it. It'll bounce back up. Okay, so that's how you could know graphically, but we're going to get more into that tomorrow. Okay? Okay. So we know that there's a little bit more to it than just plunking in these two numbers that multiply negative 10 and add to 1. Okay? Now, in fact, the two zeros, if this were a polynomial function, the zeros are, let's see, negative 1/2 and 5. Okay, if we set 2x plus 1 equal to 0, that 0 would be negative 1/2. And if we set x minus 5 equal to 0, the 0 is 5. Okay, so we're not getting integral values anymore, at least for one of them. We have a rational value. Okay, so we're going to move on to the rational zero theorem. Okay, so the rational theorem, zero theorem states that if x equals a is a root of a polynomial, p of x. Okay, like for example, when I had that last one, 2x plus 1 times x minus 5, negative 1/2 is a root, because it's the value of x that makes the polynomial 0. 5 is also a root. Okay. Then the possible a values are, okay, so they take the form of a rational number. P over Q, where P are factors of the constant, over Q, Q are factors of the leading coefficient. So factors of the constant over factors of the leading coefficient. Now, this is actually true if the leading coefficient is 1 as well, except that all of the factors of the leading coefficient are 1. So what we end up with is factors of the constant over 1, which is just factors of the constant. Okay? Now, if we think about what I just showed you in the previous example with this quadratic, okay, the actual zeros were -1/2 and 5. If you think of the factors of the of the constant rather, that would be plus or minus 1 or plus or minus 5 over possibilities here are plus or minus 1 or plus or minus 2. So this -1/2 is -1 over 2. Okay? So just to kind of get a sense of how this will work, let's list the possible zeros of this function. Okay, the zeros are the values of x that make it 0. Okay, so the constant is -9. What are the factors of 9 or negative? It doesn't actually matter what the sign is because it could be plus or minus. Because if you have -9, you're going to multiply a positive and a negative anyway. If you have +9, you could get there by multiplying two negative values. Okay, so what are the factors of 9? Yeah, so plus or minus 1, plus or minus 3, or plus or minus 9. That's a 3. Okay, over. What are the factors of 5? Plus or minus 1, plus or minus 5. Okay, now this is a little bit, we actually want to list a set of numbers. We don't just want this sort of list of possible numerators and possible denominators. So what I like to do is I go through them one at a time with each denominator. So plus or minus 1 over plus or minus 1 is plus or minus 1. Okay? Plus or minus 3 over plus or minus 1, also plus or minus 3. Okay? Plus or minus 9 over plus or minus 1 is plus or minus 9. Okay? Then we have to do the same thing with all of the other, with the other denominator of 5. So plus or minus 1 over plus or minus 5. So that's plus or minus 1/5. Okay? Plus or minus 3 over plus or minus 5, plus or minus 3/5. And then finally, plus or minus 9 over plus or minus 5, which is plus or minus 9/5. Okay, so all together, there are, let's see, 6, so 12 possibilities if you take into account the positive and the negative. Okay. Now, if I were to give this to you and made all of the roots fractions, that would be really mean. I could, but it would be mean. Wouldn't be very kind. But remember, again, we're going to be using the graph to help us as well. But we do have to show the process of what could we try, what could work, etc. Okay, so let's try it. Okay. Fully factor this polynomial, this trinomial. Okay, so we're going to start with possible a values.
1, 2, plus
1.
Okay, is that it? Leading coefficient is 1. Over plus or minus 1 or plus or minus 3. Okay, So if we actually make a list of distinct values, if you divide by plus or minus 1, you just get everything in the numerator. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then we have to take these one at a time and divide by the denominator. So plus or minus 1 over 3, plus or minus 2 over 3. Okay. Now the other ones we've actually already got down there, because plus or minus 3 over 3 is plus or minus 1, which is already there. And plus or minus 6 over 3 is plus or minus 2. Okay, so part of the process is showing what could work. Okay, now we're going to get help with this by graphing it. Okay, so it was 3x cubed.
Minus 4x squared.
Thank you. Minus
17x.
4x squared. Minus 17x.
Yeah, plus 6.
Plus 6. Okay? And I'm going to graph that. Okay. Now I can actually see from the graph, looks like 2 of these are integers, and one of them is not. So I'm going to choose one of the integers when I'm plugging it in, because that's going to make life a lot easier. So it looks like I could use -2 or 3. Okay, so pick either one of those. What you need to show is if I look at p of 3, then I'm going to get a value of 0, which tells me that x minus 3 is a factor. So that's 3 times 3 cubed minus 4 times 3 squared minus 17 times 3 plus 6, which is 3 to the 4 is 81, minus 4 times 9, 36, minus 51 plus 6. And that is 0. Okay? That's the second piece. So now what I know from this is x minus 3 is a factor. Okay, so where do I go from there? Yeah, synthetic division. I want to see, well, if I factor that out, what's left? Because I have to work with that. So in step 3, we're going to use the fact that we know that that's a factor to take it out. 3, -4, -17, and 6. Okay, so let's see. Okay, 3 times -3, -9, subtract 5. 3 times -3, negative. What did I do here? Oh, no, sorry, I'm just not done yet. Huh. Okay, I was looking to get 0 here. Okay, -17 minus -15 is -2. -2 times -3 is 6. Okay, so what I know from the third step is that my partially factored polynomial is x minus 3 times, these are the coefficients of what's left. 3x squared plus 5x minus 2. Okay, and once it's a quadratic, you don't have to use the factor theorem anymore. Okay, you can just factor that. And this guy, x minus 3, I'm going to do it very squishy. Okay, well, one of them is 3x and 3x. Sorry, 3x and x. We know what one of the other zeros is, right? What was it? I can't remember. -2, right? Was it? Yeah, -2. So x plus 2 is a factor. That can help me factor as well. X minus 3. I know another one is going to be x plus 2. So this has to be x times 3x is 3x squared, and then 2 times -1 is -2. right? Because the first two and the last two terms give you the leading coefficient and the constant. What's that? Yes, yes. Yeah. So look, you don't have to show me your work for factoring quadratics. Okay? So if you want to use the graph to do that part, go ahead. Because honestly, when you're factoring this, a lot of people do it in their head or use guess and check anyway, right? So you don't have to use a process for that. You do have to show a process for anything that's higher than a quadratic, okay? Unless, like, let's say there's a GCF of x, you could take that out, that's okay. But that's like 10C factoring. Okay. Last question of the day. A form that is used to make large rectangular blocks of ice comes in different dimensions, such as the volume, V, in cubic centimeters, such that the volume in cubic centimeters of each block can be modeled with this polynomial function, v of x equals x cubed plus 7x squared plus 16x plus 12, where x is in centimeters. Determine the possible dimensions of x that result in this volume. Okay, so if we want to know the dimensions, what are we going to have to do? Volume of a rectangular prism. Length times width times height. So if we want to know those dimensions, what are we going to have to do with this volume? Factor it. Okay, you guys try this one.